Hello everybody, my name is Ethan. Welcome back to the channel where today we are hopping back into the machine learning course on Codecademy. In today's video, we are going to be going into regularization in machine learning. We did a little bit of this very early on in this course. And in the previous video, we finished the support vector machines. So if you missed that, be sure to go check that out. We're going to now start doing regularization. So we're going to have a hard time struggle through regularization a lot today. So it plays a very important role in real-world implementations of machine learning models. It is a statistical technique that minimizes overfitting and is executed during the model fitting step. It is also embedded feature selection method because it is implemented while the parameters of the model are being calculated. So it is a technique for minimizing overfitting, and it's also a feature selection method, right? So machine learning algorithms are rarely deployed to production without some form of regularization. The reason for this is as follows. In practice, every model has to deal with the question of how well it can generalize from known to unknown data. We can train, test, and tune models based on known data and then make them as accurate as possible. However, in deploying models, we are applying them on new data. Regularization makes sure that our model is still accurate. In this lesson, we are going to learn how regularization minimizes overfitting and how to use it as a feature selection method. Along the way, we are also going to learn two concepts that are very relevant to regularization and important just as standalone topics within machine learning, namely the bias variance trade-off and the hyperparameter tuning. But first, we're going to answer the question, what is overfitting? In the image to the right, we have three curves. So it's going to be a little bit tricky to see it. I am going to for this, I'm going to move my webcam so you guys can see it. I guess I can move it down below. This is fine. You can see the three here. So it's asking us in the image to the right, we have three curves generated by different models fit to the same data. Can you identify which one of these might be underfitting and overfitting the data? Fill in the number corresponding to the plots that best matches these on the code editor. So we have the first one that is just a straight line. We have a nice curved line and then a wiggly line that's kind of going over. So I would say that the number 3 is definitely overfitting, right? So I'll say number 3 is overfitting. So which one's underfitting, 1 or 2? Well, it looks like number 1 is at underfitting because we have a lot of this, whereas number 2, you're kind of actually fitting to the curve. So I'm going to say number 1 is overfitting, or underfitting, I mean. I will now move this back. So there we go. All right, what is overfitting? It may have been pretty apparent which of these three curves in the previous exercise overfit the data set of points. However, often we have too many features to be able to visually assess if our model is overfitting our data or not. And so we need to qualify what we mean by overfitting exactly. If a model is able to represent a particular set of data points effectively, but is not able to fit new data well, it is overfitting the data. Such a model has one or more of the following attributes. It fits the training data well, but performs significantly worse on the test data. It typically has more parameters than necessary, i.e. it has high model complexity. It might be fitting for features that are multicollinear, i.e. features that are highly negative or positively correlated. It may be fitting the noise in the data and likely mistaking the noise for features. In practice, we often catch overfitting by comparing the model performance on the training data versus the test data. For instance, if the R-squared score is high for training data, but the model performs poorly on test data, it's a strong indicator of overfitting. We're going to look at one such example now. A dataset has been loaded for you from the UCI machine learning repository that describes the performance in mathematics of students from 2 Portuguese schools. We're going to implement a multilinear regression model to predict the final grade of the students based on a number of features in the dataset. We've implemented some code to print the first 5 rows, set the target variable as y and the predictor variables as the matrix capital X, calculate the number of features in the dataset, save it as num features, and press run. Okay, so right now we have number of features is equal to none. We want to calculate the number of features in the actual data set. We can probably do that by just doing length of data frame. Or it might be, actually, we can probably do length of data frame dot columns, I think is what we can do. And I don't think columns is a function. Is that how we would maybe do it? Oh, it's just x dot columns. Okay. So I was close. Note that the number of features is equal to the number of columns in X. That's obviously my bad. If we did dataframe.columns, it's also going to include this final grade as a part of it. So it would say that we had 42 features, when in fact that 42nd feature is the variable that we're kind of looking after. So, which makes sense, obviously. So we're about to fit the data to a model with 42 parameters, intercept plus 41 coefficients, one for each predictor variable. This may already make us apprehensive of the model potentially overfitting the data because the model likely has a high degree of complexity, and we haven't checked for collinearity between the features. In order to assess whether we are overfitting, we are going to fit the model. In the workspace, you'll see what we've provided, the code to split the data into a test and training set. And calculated the mean squared error on the training data in the section below the comment. Number 2, testing error. Fill in the code to calculate the MSE for the test set, currently set to none. So to do that, it doesn't actually tell us how to do that, and I'm assuming we should know how to do that, but I'm not off the top of my head do I know what the value of the mean squared error, how to calculate that is. So np dot, when we do np, where's the np coming from? I'd like to know these things. See, np is nowhere. So predicted test for the test data. Okay, we can do, oh, I see, numpy.mean, and then predicted, I see, test. I didn't check above. I'm assume we imported numpy. Yep, and numpy is np. Makes sense to me. Why tests? Oop, come on. And then we raise that to the power of 2. All right, we can see that the error on the test data is almost double the error with the training data. This is definitely an indicator of overfitting. We're now going to check the coefficients evaluated by the model to see if we can catch this. Uncomment the plotting code below with the comment number 3. And run, press run to plot the values of the coefficients produced. We see that there are a few negatively correlated coefficients here, coefficients with roughly similar values mirrored about the axis, which is of course a sign of overfitting. We will uncomment these lines here that if we show in our training error, we ended up getting an MSE of 2.6, but the testing error ended up having an MSE of 4.9. So that's obviously something. I guess we could have also looked up here and seen that the training error was that. So we didn't need to look at the hint there, but we can now see that, yep, some of them are definitely negatively correlated. Looks like G2 seems to be the biggest coefficient, but we're not 100% sure at what G2 is. All right, the loss function. Let's revisit how coefficients or parameters of a linear regression model are obtained. Suppose we want to fit a linear regression with 2 features, x1 and x2. We would get y is equal to b0 plus b1 times x1 plus b2 times x2 plus e, where e is obviously the error. We solve for the intercept b0 and coefficients b1 and b2 by minimizing the mean squared error. This is also referred to as the loss function, or alternatively as the objective function or cost function in machine learning. Loss function is equal to 1 over n times the sum of from I equals 1 to n of y to the power y subscript I minus b0 minus b1 times x1i minus b2 times x2i to the power of 2. All right, the loss function is minimized by the method of ordinary least squares, or OLS, and for larger data sets, the gradient descent algorithm is used to arrive at the minimum. As we have seen already, however, the best fit as obtained by minimizing the loss function may not be the fit that generalizes well to new data. Regularization modifies the loss function in a way that might help us with this. Before going into more detail, we're going to plot the loss function as a function of the coefficient b1 and b2. For this, we're going to generate a data set for 2-feature linear regression using the datasets module from scikit-learn. The default data generated by this module is centered, meaning that our intercept b0 is already set at 0. All right, we've written some code here to generate our data for the 2-feature scenario. The n samples input parameter lets us set how many data points we'd like. We've set it to 100, and features lets us specify the number of features, which would be 2 in our case. The coefficient equals true. Attribute gives us the coefficients generated by fitting the linear regression model. Print the coefficients given by this model. Remember that the intercept b0 is 0 as the data is centered, so we're printing the best fit values of b1 and b2 here. So it wants me to print the coefficients, which would be x1 and x2, right? So we can print x1 and then print oh my god, we're having trouble typing today. I can already tell. Print x1 and x2. I love when it asks me, did you print the coefficients? I thought I did, but maybe we just print coefficients. Coefficients. Try that instead. There we go. We're going to write a Pythonic function to output the value of the loss function at each data point for all possible values of b1 and b2. Fill in the code for the loss function, so we want to do this, so that the output loss, according to the formula below, is equal to 1 over n. All right, note that we've done some work for you, but you need to fill in the code. Calculate the error variable inside the function. So calculating the error variable can be obtained using, where's this? So we just use the error variable when b0 is equal to 0. Okay, so it would be equal to y minus b1 times x1 star minus I think we don't multiply. I think we just follow this along. I think it's doing these stars for who knows what reason. So instead what we'll do is, I think that b1 times x1 is correct, but then we would minus b2 times x2. Okay. So then if we run it, is it fine now? Yep. A script plot loss pi has been loaded for you in the workspace. It takes the values of the coefficients as inputs to a function to output the loss as a contour plot. Uncomment the lines below. So it wants us to uncomment contour plot and plot.show. Uncomment and then press run to see what it looks like. Each ellipse in this plot represents the points where the loss function has the same value. The larger ellipse, the higher the value of loss for all the points, b1 and b2, that fall in the ellipse, as we can see from the labels on the contours. Following this logic, the center of this set of concentric ellipses should represent the minimum value of the loss function, and the value of the coefficients b1 and b2 at this point should be the solution of the regression problem and represent the best fit in our data. Let's check if this is so by plotting the coefficients we obtained earlier. Complete the code under plot the best fit coefficients to overplot the best fit coefficients values. You'll have to scroll down to see the new plot. So I would assume that we now want best fit B1 to be 75, and we want this to be 24 maybe. And then we can uncomment this, show it. And as it loads, we can scroll down and see that now we're there. Cool. No, I didn't. Coefficients at index 0. This is just going to then be a coefficients at index 1. Cool. Nice. Okay, the regularization term. Regularization penalizes models for overfitting by adding a penalty term to the loss function. The two most commonly used ways of doing this are known as lasso or L1 and ridge or L2 regularization. We'll explain the meaning behind these names in a moment. Both of these rely on penalizing overfitting by controlling how large the coefficients can get in the first place. The penalty term or regularization term is multiplied by factor alpha that is then added to the old loss function as below. New loss function is equal to the old loss function plus alpha times the regularization term. Because of the additive term, minimizing the new loss function will necessarily mean true loss goes up, i.e. the scores on this will be lower on the training data than regularization without regularization. But this is what we want when we are regularizing. Remember that the reason we're regularizing is because our model is overfitted to our data, i.e. it is performing well on the training data but does not generalize well on test data. The regularization term is the sum of the absolute value of the coefficients in case of L1 regularization and the sum of the squares of the coefficients in the case of L2. L1 regularization term is the absolute value of B1 plus the absolute value of B2. And L2 regularization is B1 squared plus B2 squared. In mathematics, the sum of the magnitudes of a vector is known as L1 norm related to Manhattan distance, and the square root of the sum of the magnitudes or the Euclidean distance from the origin is known as the L2 norm, and that's the reason for both names of both methods, right? All right, L1 or lasso regularization. In the case of the two-feature linear regression scenario we were looking at in the previous exercise, our new loss function for L1 regularization looks as follows. I'm not even going to read that out. Minimizing this new loss function essentially means restricting the size of the regularization term while minimizing the old loss function. Let's say that our regularization term can take a maximum value S. This is equivalent to confining our coefficients to a surface around the origin bounded by 4 lines. B1 plus B2 is equal to S. B1 minus B2 is equal to S. Okay. The figure to the right replicates the elliptic contours for the loss function that we plotted earlier in the lesson. If we plot these 4 lines as with B1 and B2 as X and Y axes respectively, we get the diamond-shaped blue shaded region that we've shown here. We've chosen a value of S equals 50 for this figure. This means that either coefficient can have a maximum value of 50. The choice of S is deeply tied to the choice of alpha as they are inversely related. The value of B1 that satisfies the regularization constraint while minimizing the loss function is denoted by the white dot. Notice that this is exactly the tip of the diamond where it intersects with the contour from our loss function. It also happens to fall exactly on the x-axis and thus setting up the value of B2 to 0. This is why the point that minimizes the new why is this the point that minimizes the new loss function? Remember that the goal here is to minimize the original loss function while meeting the regularization constraint. We still want to be as close to the center of the contours, the original loss function minimum, as possible. The point that's close to the center of the contours while simultaneously lying within the regularization surface boundary is the white dot. The word lasso is actually an acronym for least absolute shrinkage and selection operator. It shrinks the absolute value of the coefficients and selects parameters by way of setting some of the coefficients to 0. If the coefficient of a regression model is set to 0, it means that we've pretty much eliminated the feature associated with it. In models with a higher number of features, lasso regularization tends to set a significant fractions of its parameters to 0, thus acting as a feature selection method. Lasso regularization continued. We've covered the basics of how lasso regularization minimizes overfitting and simultaneously acts as a feature selection method using a two-feature example. How does it extend to a multiple feature dataset? The loss function for a multiple linear regression case with m features looks as follows. You can use the horizontal bar to scroll to view the entire equation. It's not giving me that, so I assume this is the entire equation, but we just add the b values as far as we go, right? All right, we're going to examine this by reapplying a multilinear regression model to the student performance data set we were looking on earlier on this lesson. Only this time we're going to do this with L1 regularization. A quick reminder that our original unregularized coefficients look as shown in this image right here. Regression coefficients. We've loaded in a file, script.py, here containing the analysis we did earlier on. Some of the things we noted earlier were that there was too many features, possibly, from the number of columns in the data frame. Testing error is higher than the training error by looking at the MSE, and it's highly negative. There are highly negatively correlated features inferred from the plot of the coefficient. So a couple of errors that kind of lead to overfitting. So let's use this lasso method of regularization. We can implement lasso for this dataset by importing the lasso module within scikit-learn's class of linear models. We're choosing a value of s by setting alpha equal to 0.1. The scikit-learn default is 1. We've written some code in script.py to do a train test split. Implement regression with lasso regularization, then calculate the training error. Press run to view the results. So it has... I'm not sure if it's actually implemented the lasso or not because it doesn't say. Right here. We've imported lasso, so first we split it up. We then create a lasso object that has the value of alpha equals 1 or 0.1. Value of s by setting alpha equal to 0.1. Next, what it wants us to do is train to split, flitting. Okay. It looks like it's done all the work for me, so I think all I have to do is press run and it'll work. Yep. So when we calculate our lasso L1 training error, we get 3.01. And now if we follow the syntax for training error, calculate the testing error of the following using the following steps. We set the variable L1 predicted test equal to the result of applying the model to X test. So lasso dot by applying the model. So okay, lasso dot predict X underscore test. Let's calculate the mean squared error again. Let's see if I remember it off the top of my head. I think it's the predicted minus the actual times to the power 2. Yep. So it would be L1 underscore predicted underscore test minus Y test to the power of 2. And then it wants us to print L1 underscore MSC underscore test. I guess what I can do is do a nice little syntax here like they have. So we'll do lasso L1 MSC oopsie doopsie. So now when it prints it out, Just going to get rid of it. I don't know why that's causing an error. Okay, we now see how our training error went up, but our test error went down, which makes sense, as our model is performing slightly better on test data at the cost of performing slightly worse on training data. What do our coefficients look like post lasso regularization? Uncomment the lines below. Number 3 here. And I didn't add, no, I did not add plt.show. And now, a lot of the parameters were set to 0. So we've kept some of the bigger ones, but we've done that. Lasso has shrunk more than half of our coefficients to 0. Additionally, while the value of all coefficients has shrunk, Lasso has increased the relative importance of some. An important thing to note here is that we manually set the alpha of to equal to 0.1. The number of features that get eliminated due to Lasso is definitely tied to the value of alpha. We're going to examine this more after we cover the basics of L2 or ridge regularization. Just for fun, let's change this value of alpha to 1 and see what happens. We ended up only keeping our positive values, so that's pretty interesting. We'll see about that. All right, L2 or ridge regularization. L2 regularization is also called ridge regularization, as the mathematical formulation of it belongs to a class of analysis methods known as ridge analysis. The modified loss function in the case of L2 regularization looks as follows. L2 loss is equal to, there you go. Similar to L1, this would mean constraining the regularization term to be the following surface. B1 squared plus B2 squared is less than S squared. The key difference here is that instead of the diamond-shaped area, we're constraining the coefficients to live within a circle of radius S, as shown in the figure here. The general goal is still similar, though. We want to minimize the old loss while restricting the values of the coefficients to the boundary of this circle. Once again, we want our new coefficient values to be as close to the unregularized best fit solution, i.e. the center of the contours, as possible while falling within the circle. The values of B1 and B2 that minimize this new loss function almost never lie on either axis. The solution here is not the pink dot that lies on the x-axis like in L1, but rather the white dot that we have shown. The reason for this is as follows. The circle that contains the white and pink dot represent the smallest value of old loss function that satisfies the regularization constraint. But while the pink dot makes the regularization term's value s to the power of 2 exactly, the white dot makes it even smaller as it lies inside the circle. Unlike lasso, our ridge coefficients can never be exactly 0. L2 regularization is therefore not a feature elimination method like L1. The coefficients of L2 get arbitrarily small but never 0. This is particularly useful when we don't want to get rid of features during modeling, but nonetheless their relative importance is emphasized. Ridge regularization, we're now going to apply L2 regularization on student performances data set we've been working on and see how many feature scenario. The loss function for multiple linear regression with L2 features is this. We're going to examine this by reapplying a multilinear regression model to the student performance data set. Again, we had these testing errors, right? Similar to our L1 exercise, we've loaded the file here containing the analysis we did. We're going to first set the, it wants us to first set a variable L1 equal to the result of applying the model to test. So we can do that by doing, is the actual, it's ridge.predict x test. We're going to do np.mean, and then what we do L2 pred test minus y test to the power of 2. Okay. The training and test mean square errors obtained from implementing the regression without regularization were 2.6 and 4.9, rounded to 3 decimals respectively. We want to see how our training error went up, but our last test error went down, which makes sense as our model is performing slightly better on test data at the cost of performing slightly worse on the training data. What do our coefficients look like post-ridge regularization? We can do this. Look at this by commenting these lines and then doing a plt.show. And we see that a lot of them, if we look at the original, this is what it looked like. The new one looks more like this. So, all right, hyperparameter tuning. Alpha is known is what is known as the hyperparameter in machine learning. It is not learned during the model fitting step the way model parameters are. Rather, it's chosen prior to fitting the model and is used to control the learning process. In regularization, the choice of alpha determines how much we want to control for overfitting during the model fitting step. We're able to do this by using alpha to control the size of the constraint surface and consequently the size of the coefficients themselves. The larger the alpha, the smaller the size of the allowed coefficients. In essence, alpha is inversely proportional to S in the case of L1 regularization, or S to the power of 2 in case of L2 regularization. Consider all the possible choices in terms of the size of the constraints boundaries for both types of regularization. In the figures shown to the right, the blue diamonds and the red circles represent the possible choices for S. As we can see, the button less regularization increases S, and the button more regularization decreases S. If S is very large, i.e. alpha is very small, the unregularized loss function minimum can easily fall within the large boundary and thus make it similar to regression without regularization. If S is very small, i.e. alpha is very large, the regression coefficients become very small, and the loss for best fit becomes large, making the regression over-regularized. To avoid either of these extreme scenarios, we want to find a right amount. Kind of the theme of machine learning and doing these testing is kind of finding the Goldilocks of all of it by tuning alpha, and this process is known as hyperparameter tuning. The bias variance trade-off. When we add the regularization term to our loss function, we are in essence introducing a bias into our problem. When we are biasing our model to have coefficients with regularization boundary, the greater the alpha, the smaller the coefficients, and the more biased the model. The animation to the right shows the coefficients obtained from both types of regularization on the student performance data set we've been working with throughout the lesson. Using the navigation buttons, we can see what happens when the coefficients we increase and decrease alpha for very high values of alpha. While ridge begins to make most of the coefficients very small, lasso ends up eliminating almost all but one feature. And that's obviously the last big one right there that ends up becoming worth 100% of the data set, right? So pretty interesting. Ideally, we want a machine learning model to have a low bias and low variance, i.e. we want it to perform well on training data as well as test data. However, trying to minimize bias and variance simultaneously is a bit of a conundrum, and lowering one raises the other. This dilemma in machine learning models is known as the bias variance trade-off. Hyperparameter tuning helps us find a sweet spot in this trade-off by ensuring that neither bias nor variance get too high. Typically, a portion of the data set is set aside and is known as validation set or holdout set over and above the usual test-train split. And this is used to perform hyperparameter tuning. We will dive into the ways we can implement this in scikit-learn in the following lesson. All right, review. In this lesson, we've learned the following topics: importance of regularization, lasso and ridge regularization, how to implement them, how regularization can be used as a feature selection method, and hyperparameter tuning, and the various bias variance trade-off. Very nice. Which of these statements is false? Hyperparameters are learned in the data set. I already think this one's false. A model that performs well on training data is said to have high variance. Yep. Increasing the bias in a machine lowers the variance. Yep. Regularization parameter. Yeah, it's just this one. Okay. Complete the following piece of code that implements L1 regularization on dataset X and Y and calculates the mean squared error of the fit. Okay, so from scikit-learn, we want to do lasso. So we're going to import lasso. Then we'll create a lasso object. We can call it model. and we're going to set alpha equal to 0.1, then we'll do a model.fit, and after that we'll do a model.predict. Cool. Which of the following statements about regularization is false? It corrects for overfitting. It is executed before implementing a machine learning model. L1 regularization is known as lasso. Imposes a constraint on the size of the coefficients. It's executed before implementing. Regularization corrects overfitting by imposing a constraint. It can also, yeah, I guess that's true. Increasing the value of the hyperparameter alpha in regularization is the same as increasing training error, increasing the size of regulation. This is incorrect because alpha is inversely proportional to the size of regulation. Not great, guys. Which of the following statements is true? L2 regularization can also function as a feature elimination method. Yeah. Consider the following 3-parameter linear regression model. The ridge regularization term for this model would be p squared plus b. Yeah. Fill in the following paragraph about loss functions. Regularization for linear regression is implemented by modifying the loss function and adding a term to it. This term is a product of blank that controls the strength and of the regularization. In the case of L1 is absolute value is the sum of the squared values. That's L2. Meaning that the old loss goes is also referred to as the blank term, overfitting term. So minimizing this loss function means that the value of the old loss goes, and that's the reason this additive term is also referred to as minimizing. Okay, wait. Regularization for linear regression is implemented by modifying the loss function by adding a term to it. This term is the product of a hyperparameter that controls the strength. The regularization term is the sum squared in the case of L2 and the absolute values in the case of L1. Minimizing this loss function means that the value of the old loss goes down. Overfitting term. The old loss value will go up. Cool. Very fun. Okay, the following piece of code has 3 functions to implement ridge regularization with the parameter. Fill in the code. I think I'm gonna have to, yeah, I'm gonna have to retake it. Okay, that's always amazing to have to retake it. I don't remember. Increasing the training error. Increasing the value of the hyperparameter alpha in regularization is the same as Which of the following statements is true? Feature selection method. Ridge regularization is P1. Okay, so it goes up. And it's not called the overfitting term. Hyperparameter squared values is L2. This value is L1. Is also, that's why the reason, and that's the reason this additive term is also referred to as a lost term, penalty term. Never heard of it. Cool. We might lose again. Ridge regularization term would just be that. And then alpha. Alright, cool. Really fun one today, guys. Here is some information about implementing it in Python with linear regression, and this is going to specifically be using the scikit-learn, as it mentioned earlier. I'm not going to go through this because it's not an actual part of doing it in Python. So I'm just going to continue on, and think we probably have a project here, which is perfectly fine. And then next we'll go into more hyperparameter stuff, so we'll do that in a separate video. Predict wine quality with regularization. The data you're going to be working with is from the wine quality dataset in the UCI machine learning repository. We're looking at the red wine data in particular, and while the original dataset has a 1 to 10 rating, we've made the classification problem with a wine quality of good being greater than 5 and bad being equal than or less than 5. So implement different logistic regression classifiers, find the best ridge regularized classifier using hyperparameter tuning, and implement tuned lasso regularization. Before we begin modeling, let's scale our data using standard scaler. Data transformation, we'll say scalar is equal to standard scalar object, and then we can do, it wants me to, I guess we don't have to make an object, we can just do standard scalar dot fit to the features, and then we can do standard scalar dot transform to get x to get to the transported x. Standard scalar fit is equal. See, this is what I wanted to do anyways. So scalar is equal to, I'm just going to do it this way. This is the way I know. Standard scalar dot fit then we can fit it to the features, and then we can say x is equal to scalar dot transform the features. Alright, it wants me to perform an 80-20 train test split on the data, set the random state to 99 for reproducibility. We can do that. We'll set the variables equal to x train, x test, y train, y test is equal to train test split, and it takes in two things, right? Yeah, that's right. Okay, so x, y test size is equal to 0.2, and then random state is equal to 99. Okay, cool. All right, fit the logistic without regularization. Define a classifier CLF no reg is equal to logistic regression. And then we can do CLF no reg is equal to dot fit. And we're going to fit it to the training data, so we'll do X train and Y train. And that should be correct, right? And I must have did a spelling error here. Logistic. Am I saying that? Am I doing that right? Logistic. I think that's correct now. Yeah, nice. Okay. What is it wanting me to do here also? Why is it saying remember to set the penalty parameter equal to none? Glad I looked that up, because where have I ever learned that is my question. Okay, we're now going to, I guess I'll save. We're now going to plot the coefficients obtained from fitting the logistic regression model. Copy and paste the following code to get the ordered coefficients as a bar plot. We'll see if it lets me copy and paste it. Sometimes it does, sometimes it doesn't. Today is one of those days where it doesn't let me. So predictors is equal to features dot columns. We'll say coefficients is equal to CLF no reg dot coefficient underscore dot ravel. We'll then do coefficient is equal to PD dot series, creating a pandas series, coefficients predictors dot sort values, coefficient dot plot kind equal bar, title equal coefficients no regularization, PLT dot tight layout PLT dot show PLD dot CLF. Cool. You're now ready to evaluate this classifier. In the case of linear regression, we evaluated our models using a mean squared error. For classifiers, it's important that the classifier not only have high accuracy, but also high precision and recall, i.e. low false positive and low false negative rates. A metric known as an F1 score, which is the weighted mean of precision and recall, captures this performance as a classifier. Holistically, it takes the values between 0 and 1, the closer it is to 1, better classifier, using F1 score to calculate the F1 score of the training and test data. Okay. So F1 score, the values of X test, Y test, and then what? F1 score with X train and Y train. I assume that's what it wants us to do. Okay. So Y predict test is equal to CLF. No. I'm confused. Did it say this in it? Now we're ready to classify F1 scores, and it just introduces the concept of it and says calculate it. Okay, so we needed to know to first calculate the predicted test. So we first predict it based on the test and train data. Y predict train is equal to CLF. No regularization.predict x train y train y predicted train y test y predict test. And now we can wrap these individually in a print statement. Where we also put training score, or sorry, this should be testing score. We'll do the exact same thing for this one up here, where we wrap it in a print statement and put training score. Logistic regression and L2 regularization. We've seen in the previous article that the default implementation of logistic regression in scikit-learn is ridge regularized. Use this default implementation to implement a classifier CLF default that is L2 regularized. Okay, so in number 6, we want to just do the default implementation. So from scikit sk, it's usually sklearn import bridge. Is that what it is? What are we doing here? We've seen the previous article that the default implementation is ridge regularized. Use the default. Oh. So it already is CLF. I'm struggling today, guys. I don't know what it is. Logistic regression. CLF dot default. And the y train variable. Okay, obtain the training and test F1 score for the ridge regularized using the code similar to what we have in test 5. Notice if either score goes up or down. So it wants me to do it again, but use the default. So did we change the variable name at least? Nope. But instead of this, we'll do CLF default dot predict. Okay, when we do it, it looks like the training score, it looks like nothing changed, to be honest. So, I don't know. The score remains the same. Does this mean that regularization did nothing? Indeed. This means that the constraint boundary for the regularization we performed is large enough to hold the original loss function minimum, thus rendering our model the same as the unregularized one. How can we tune up the regularization? Recall that C is the inverse of the regularization strength alpha, meaning the smaller value of C corresponds to more regularization. In scikit-learn, default for C is 1, therefore in order to increase the amount of regularization, we need to consider values of C that are less than 1, but how far do we need to try? Lovely. Let's define an array C, array that takes value of C, get an array for each of the training tests corresponding to the values of C. Okay, so for how do we even change the C value? I don't even see where it goes in. It's good. It would be a for loop, right? So for something in C. My goodness. Okay, for X in. Yeah, see, I kind of figured it was going to be something like that, so I'm glad I just kind of skipping this, because this is just a bunch of, yeah. Where C is equal to X. Then, we predict both values. Okay, so we do CLF dot fit using the values of X train and Y train. So we've now fit our model. Next, we're going to predict both values of train score is equal to CLF dot predict using is this what they do? Oh my lord. Yeah, X test and X train test scores equal to CLF dot predict using X test. Then training array dot depend F1 score Y train Y predicted train test array dot append F1 score Y test and Y predicted test. All right. Use the following plotting code to plot the training and test scores of a function C. Does this clarify the C's range? It doesn't need to find a range to search for. Using the following plotting code to plot the training test scores. Let me see if it'll let me copy this one. Nope. Let me reload it and see what happens. Maybe it'll let me do it now. Nope. I love when it says copy paste and you just physically cannot. And that's been an issue for a long time. plt.plot. I get like you not wanting people to just copy and paste all of their work, but when it asks you to copy and paste your work, kind of annoying when we can't. After this, I'm going to end the video just because this has been an interesting project where I don't even know if I'm quite following along. Obviously, not what you want when you're doing this, but plt.x scale log and then plt.show. I definitely understand the concept, but I feel like they're doing a little bit of a, I don't want to say they're doing a bad job of explaining it, but I'm just not picking it up, I think. When we do plt.show, there you go. Who knows? This is why it's like this. 0.01. Somehow that's what I'm supposed to get from that, but I don't know. That is going to do it for today's video. If you did enjoy it, please be sure to give it a like, subscribe, and I'll see you in the next one. Peace out.